Nikolas, good to see you.
Hi, Felix. Good to see you too.
Finally, we've made it to talk about AI and AI in control systems. That's what I'm interested in. So
absolutely, looking forward to it.
Thanks for coming. So maybe a brief introduction why I'm interested. As you know, I'm responsible for TargetLink. So it's production code. It's a production code generator. So it's meant to generate code that runs on embedded systems in typically cars, so cyber physical systems. And I get increasing demand from the market, from my customers, for the use of AI technology. And so I wanted to take the opportunity to talk to your local expert in artificial intelligence to learn about the options and to get recommendations for my customers also on how to approach the topic. So thanks for being here. Thanks for meeting me. So
yeah,
would you like to introduce yourself briefly?
Yeah, I was thinking the same. So maybe it would be helpful to quickly say who we are, right? So like you mentioned, I'm at dSPACE. My role is manager for AI. So I'm very much in the AI space, doing development with neural networks, also in the automotive setting. So processing camera data, LiDAR data, etc. My background is in AI and robotics. That's where I'm coming from as a background. Yeah, but I must say, I mean, I've started MATLAB, I've seen Simulink, but I'm absolutely not an expert at all when it comes to model-based design, right? So for me, I think some of the questions I'm really curious to hear what you would ask, what you have in mind, maybe about the combination model-based design plus AI. What we are going to talk about. Very curious and very happy to speak to you today.
Yeah, thanks for being here, as I've said. So actually, when I think AI and what you told me on lunches, etc., then I always hear kind of big GPUs that are needed. And this somehow doesn't match my world where everything is tiny. The microcontrollers have a few kilobytes or maybe a megabyte of RAM, and then that everything needs to fit into ROM. And so I was nothing. Is this something that you also deal with, that you also see that people want to use AI on those small systems?
Sure. So maybe just a few remarks on that to maybe get things really clear here. So basically, when we deal with AI, right, we are dealing with, let's say, different phases of developing an AI as well. So we are starting with the training, right? So AI is something which we are training based on lots of data which we've collected, and doing the data crunching and the training, that's when we really need these large graphic cards clusters, right? GPU clusters, depending on the size of your training, really big ones, GPUs being used in parallel for a long time, right? This is the training side when we are developing the AI. Once we're done with that, then we're talking about a bit of a different story. And it's going to be less demanding in terms of compute, which we require, right? So a trained AI is something which you can also run fairly efficiently, depending on the size of your AI model, right?
This, of course, all goes into dimensions that for embedded systems seem quite huge, like you mentioned, 10 to 100 million, right? Parameters, so they would need to be somehow stored. If a parameter is a standard double number, then that would be 80 to 100 million bytes.
Yes, but keep in mind we're talking about
100 megabytes, something like that.
We're talking about ADAS features, right? So autonomous driving, automated driver assistance systems. So here, of course, this is, let's say, not your simplest control loop, right? So maybe if you have something,
it's not a control loop at all, right?
Well, I mean, it has to drive, right? So it has to control the car.
Okay,
it's a complex one.
Fair enough. So, okay, so what I'm wondering is, what do you do if you find out it's too large, it's too huge. Does that ever happen, or is this on the level that you're
absolutely.
working on always the case that you say, oh, well, then just add another couple of GPUs with another
Sure,
20,000 cores and fire at it?
Yeah, sure.
Probably not, right?
Well, it depends on what your use case is. Again, I mean, sorry, it always depends on your use case, right? But
that's normal.
if you aim to have your new network be on an embedded chip, on embedded hardware, and it not being very power consuming, right? Then you have to think about this a lot. Yes, so on the other side, if your use case is software as a service in the cloud, you just book 100 cloud instances with very powerful GPUs, then you don't have to care so much about it as long as you can pay for it. But yeah, so if you want to go into an embedded chip, then of course, how do I fit my new network onto this chip? That's an important question to ask, and you will be faced with it, right? And so it's actually still an active area of research. How to best do this, right? But we are talking about going from a nice and cozy GPU where I can use float 32. It's not a problem at all for me, right? I have lots of memory, and then on my target platform, I have to deal with stuff like U8, right? I don't have float 32 maybe available. So what do I do with it?
From the computational structure inside, I only talk about inference now. Is it always the same runtime typically? So if I present an input to the network and I get an output, is the network always kind of doing the same number of operations, or could it be that different inputs lead to a different execution time of the networks because there's some kind of branch somewhere inside that's taken in some cases and in other cases not? How is this typically done today? My naive expectation would be it's just one stream of computation that's also that would be in line with it's very well able to be computed on GPUs because they also are not very strong in control flow typically, and so that's the case. So that's
you see me heavily nodding. That's typically absolutely the case. And this means that we are typically we are able to say our inference time, the speed at which the neural network is able to process data. This is something that we can provide you with as information. Once we have the model implemented, we can measure that on the hardware.
So that's, of course, from a safety perspective, a very, very nice feature, because that means you can basically, in a hard real-time system, rely on an answer being there after time X.
Exactly. And this is also maybe another benefit of using a new network in these complex, difficult to model domains, right, where you have to calculate very complicated simulations, which take forever, maybe on your CPU or on your cluster, even, right? Some physical models are very complex, so there's lots of gain to be made actually in some settings where you can use a surrogate model, a neural network, which is trained on these simulation runs, right? The input and output. And then you can use this as a surrogate model for the complicated model, right? And then you could actually speed up your simulation quite a lot.
Okay.
So, are you convinced that AI plays an important role in model-based design? Do you think your customers will adopt using AI?
I think the importance will be growing, and I think it's really a good thing to do and offers many new opportunities to improve the systems. So I'm looking forward to that. But thanks for the explanations. I actually learned a lot today, which I really enjoyed.
Same from my side.
And so thank you very much.
dSPACE, your partner in simulation and validation.